So you get the idea that Earth has had all these processes going on, and still, over geologic timescales, the CO2 carbon cycle is essentially stable. I just wanted to add this for the thermohaline circulation, but you still have to go and look at other podcasts. There are special reasons why there is deep water forming here in the so-called Jin seas, Greenland, Iceland, Norwegian seas. That water sinks, and this greenish, bluish cold water flows south. There are deep waters forming in the Southern Ocean as well because of other processes of heavy density formation at the surface, slightly different than here. Lots of evaporation, salt left behind here, a lot of ice formation and salt left behind here, and so on. Those waters are inundating the Pacific and the Indian Ocean. Indian Ocean is landlocked, so the water has to convert to surface water, come back out, and go back across the equator to provide the mass for sinking. And the same here, this water goes through the Indonesian seas, called the Indonesian through flow, mixes with here, turns around a little, all kind of complicated loops happen. So I won't go into the details here, other than that really when the water sinks, it also takes down heat and other gases like oxygen and CO2 with it, so it is a big part of the carbon cycle as well. Altogether, now there are models which are able to reconstruct past climates and use various evidences for trying to validate the model from paleosols, from sediments, from other evidences which depend on how far back you can go. So here, model and proxy estimates of atmospheric CO2 concentration in deep geologic time. So this is in ppm, and you can see that if we go beyond the the Cambrian into the Proterozoic early life, the range of possible CO2 concentration is huge. So anywhere as low as 2,000 and more to 6,000 ppm or so, which is tremendously higher than what we are worrying about right now, right? We are here at 400 something this right now, and increasing by about 4 ppm parts per million by volume. So obviously Earth has seen very large CO2 atmospheric concentrations before, and yet we are talking on large, long time scales. The global carbon cycle is essentially stable. And then it dropped down here to basically the current levels or lower when the vascular plants boomed and started drawing down carbon because of photosynthesis, and created a snowball Earth. And then we went back up to the Cretaceous hothouse, and then we talked about the drop due to potentially the rise of the Himalayas and the cooling associated with that in the last 50 million years, and so on and so forth. Okay, so that's the long-term history. But there are also evidences of these big burps like the Paleocene-Eocene thermal maximum. So we are looking here at degree C ice free, so there was a jump of maybe 2 to 5 degrees in a very short time, maybe 1,000 years or a couple of thousand years. So you can see the evidences coming from oxygen isotopes from fossil foraminifera, from ocean sediment cores. We are also using delta O18 foraminiferal carbonate here. These evolved around 170 million years ago, as we saw before. And there is a nice ocean drilling program which goes and looks at how the sediments have buried geologic isotopic signatures in the past, and using all that evidence we can reconstruct these temperature anomalies. And the idea is then to figure out what would have caused such a rapid warming. Obviously some sort of a carbon increase. Is it methane or is it CO2? That has to be figured out. Plus you have to see how long it took for the system to equilibrate after such a huge perturbation, because that would have relevance for the present global warming, where we are perturbing the carbon cycle as well. So looking at the delta C13 of the calcium carbonate in parts per mil, this is data from the Paleocene-Eocene thermal maximum from Zakos et al. You can see that there was fairly rapid. Remember, these are in millions of years, so you have to be careful. Looks like a huge jump, but that's a few thousand years. And then the CO2 recovers over 100,000 years. This is the residence time of CO2 plus the way CO2 gets taken up by the ocean, by soils, gets sunk out of the system into the sediments in the ocean, and so on and so forth. So that is relevant for the current carbon cycle as well, because even if we stop emitting all the carbon right now, how long would it take for the accumulated carbon since the Industrial Revolution to equilibrate out? That's a key question as well. Okay, so this is using delta 18 oxygen of CaCO3, so delta C13 and delta O18. So temperature change is shown here. So you can see that this is a massive spike, and then it recovered over 100,000 years. So this is relevant as well. This is another way to look at it from Natural History of Smithsonian Institute. So average temperatures, so this is the pre-Paleocene, Eocene thermal maximum. So you can see the vegetation evidence here. Rapid warming into the thermal maximum, and then cooling over as we said, 100,000 year time scale, large scale vegetation changes that can be understood from the evidences, and then there is a recovery again after about 100,000 years. So this is critical. What caused this? There are many hypotheses. The one that most people like is that there are what are called methane clathrates or hydrates buried in cold, high pressure, especially coastal waters. As the organic matter is created by photosynthesis, drops in the shallow coastal waters, more drops on top, rivers bringing sediments and bury this organic matter, and then some anaerobic respiration happens, which converts the organic matter into methane. Because it's under high pressure and cold temperatures, it just becomes a like a hydrate, high concentration methane bubble, which can be dug up and held in your hand, and it's got so much methane, and so much methane is so highly oxidizable that it can just burn. Okay, you can find cute images of that, graduate students playing with it in the lab in terms of methane hydrate. So some kind of perturbation is supposed to have happened which released massive amounts of methane, which could explain this rapid increase in greenhouse effect and the warming. But that's only one of the hypotheses. There are other ideas that are used to do this as well. So we're still talking about various processes where the rock weathering thermostat can be seen as a simple version, which I think is produced by Richard Halley at Penn State. So at the surface we have the faster when warmer, silicate being weathered by CO2 dissolved in water, converting to calcium carbonate, and silica, which is used by diatoms and so on, for example. In the deep earth, when this gets buried, deep earth doesn't care about surface temperature, so you get metamorphosis at high temperature and pressure to reproduce the silicate rocks. So this cycle is what we are talking about in terms of long time scales of CO2 production and burial, and this cycle being stable despite the faster weathering cycle CO2 thermostat at the surface, where we said warmer temperatures drive higher humidity and rainfall and weathering and drawdown of CO2, and then there are other processes like volcanic activities which are also important during snowball Earth episodes, as we will see later, because that would build up the CO2 in the atmosphere to then melt the snowball Earth and so on and so forth. So despite this many complicated components involved, this is still very much a stable long-term carbon cycle. That's also seen in terms of this calcium carbonate deposition and organic carbon deposition, which are the two parts of this ocean carbon cycle versus the this silicate weathering cycle that we are talking about. As I said before, the ratio of these two seems to be steady at 1:4, and you can see the correspondence between the delta O18 signature, delta C13 and calcium carbonate signatures. So this again tells you the close coupling between oxygen cycle, organic carbon cycle, and the silica weathering cycle. So the last part that remains in this chapter is called the climate sensitivity, which we will do in the next podcast. Okay.